Good day, everyone. I am Villacrusis of BSEE 2A. Today, I am going to discuss one of the topics under the discrete probability distributions. In particular, the topic about the expected values of random variables. I am going to tackle the expected value, variance, in standard deviation, empirical rule, and Chebyshevs theorem. The learning objectives. At the end of this lesson, the student should be able to first, understand the expected values, variance, and standard deviation. Second, recognize the empirical rule and Chebyshevs theorem. And third, have a deeper knowledge about the topic through the given examples. So now, let us start the discussion with the concept of the expected value. Expected value of a discrete random variable. The expected value of a discrete random variable is also referred to as the mean of a random variable. It can be calculated as the weighted average of all the outcomes of that random variable based on their probabilities. Simply, the expected value or the mean of a discrete random variable is a weighted average of the possible values that the random variable can take. It is not the same with the sample mean of a group of observations, because the sample mean gives each observation an equal weight. The mean is found by adding all of the numbers together and then dividing by the number of items in the set. Meanwhile, the mean of a random variable weights each outcome according to its probability. The expected value or the mean of a discrete random variable having probability function is given by this formula. The mean is denoted by the Greek letter mu, so this is the mean of the random variable x. The formula means that we multiply each value in the support by its respective probability and then add them all together. It can be seen as an average value but weighted by the likelihood of the value. Simply, to calculate the expected value or the mean, take the sum of the various outcomes and weight them by their probabilities. Now, let's have various examples to better understand the expected value. Example 1, Game 1. Suppose that you and your friend are matching balance coins. Each of you tosses a coin. If the upper faces match, you win $1. If they do not match, you lose $1. The probability of a match is 1/2, and in the long run, you will win about half the time. Take note that the negative sign indicates a loss to you, while the positive sign indicates a winning to you. You win negative half the time and positive half the time for an average of 0. This average is sometimes called your expected winnings per game or the expected value of your winnings. An expected value of 0 indicates that this is a fair game. Example 2, Game 2. Now payday has arrived, and you and your friend up the stakes to $10 per game of matching coins. The new stakes can be thought of as a function of the old in the sense that if X represents winnings per game when you were playing for $1, then 10X represents your winnings per game when you play for $10. You now win -10 or +10 with equal probability. So your expected winnings per game are 0. An expected value of 0 indicates that the game is still fair. Example 3, Game 3. You and your friend decide to play the coin matching game by allowing you to win $1 if the match is tails and $2 if the match is heads. You lose $1 if the coins do not match. So your expected winnings per game are 0.25. An expected value of 0.25 indicates that this is not a fair game. So you are likely to win 25 cents per game in the long run. In other words, the game is favorable to you. Example 4, Game 4. In the coin matching game, suppose you pay your friend $1.50 if the coins do not match. You'll still win $1 if the match is tails and $2 if the match is heads. So your expected winnings per game are 0. An expected value of 0 indicates that the game is now fair. Now, the question is, what is the difference between the original Game 1 and Game 4 in which the payoffs were $1? The difference certainly cannot be explained by the expected value because both games are fair. You can win more, but you also lose more with new payoffs. The difference between the two can be partially explained in terms of the variation of your winnings across many games. We often measure variation using the variance or the standard deviation. In order to know how to measure the variation, let us now move on to the concept of variance. Variance of a discrete random variable. The variance of a random variable with expected value is given by this formula. The formula means that we subtract the expected value from the value of x and square that value and multiply that value by its probability. Then sum all of those values. Next, let us know the concept of standard deviation. Standard deviation of a discrete random variable. The standard deviation of a random variable is given by this formula. The formula means that we simply take the square root of the variance. Manipulating expected values. For any random variable x and constants a and b. This formula will be used when there are given constants. The first one is for calculating the expected value. It means that constant a will be multiplied to the expected value plus b. The second one, on the other hand, is for calculating the variance. It means that the constant a will be squared and then multiply to the variance. Let us have various examples for us to have a better understanding on the concept of variance and standard deviation. Example 1. The table provides the age distribution of the population for 1990 and 2050. Determine the mean age of 1990 and 2050. Also determine the variation in the two age distributions. Note, the numbers are percentages. Age is actually a continuous measurement, but when reported in categories, we can treat it as a discrete random variable. To move from continuous age intervals to age classes, we assign each interval the value of its midpoint. For example, the age interval 5 to 13 has a midpoint of 9, and the age interval 65 to 84 has a midpoint of 75. The data in the table are interpreted as reporting that 7.6% of the 1990 population was around 3 years of age, and 6.4% of the 2050 population is anticipated to be around 3 years of age. Solution. The mean age of 1990 is approximated by 35.5. It is calculated by multiplying each value x, which is the midpoint, in the support by its respective probability in the 1990, and then add them all together. For 2050, the mean age is approximated by 41.2. It is calculated with the same process of calculating the mean age of 1990. On the other hand, the variation for 1990 can be approximated by the standard deviation 22.5, and the variation for 2050 can be approximated by the standard deviation 26.0. It is calculated by subtracting the expected value from the value of x, then square the value and multiply the value by its probability, sum of all those values, and take the square root. The result shows that the population is not only getting older, but its variation is increasing too. Example 2. The manager of a stockroom in a factory knows from her study of records that X, the daily demand, which is the number of times used per day for a certain tool, has the following probability distribution. Find the expected daily demand for the tool and the variance. That is, 50% of the daily records showed that the tool was used one time. Solution. From the definition of expected value, we see that 1.3 is the mean, and from the definition of variance, we see that 0.41 is the variance. Example 3. In the previous example, suppose it costs the factory $100 each time the tool is used. Find the mean and the variance of the daily cost for use of this tool. Recall that X is the daily demand, then the daily cost of using this tool is 100x. This example has a given constant which is 100, so the mean is calculated by multiplying the constant with the expected value. So using the above results, the mean is 130. Using the above results, the variance is 4100. It is calculated by getting the square of the constant and multiplying it to the variance. On the other hand, using the above results, the standard deviation of daily cost is 64.03. It is calculated by getting the square root of the variance. Example 4. The operators of certain machinery are required to take a proficiency test. A national testing agency gives this test nationwide. The possible scores on the test are 0, 1, 2, 3, or 4. The test brochure published by the agency gave the following information about the scores and the corresponding probabilities. Compute the mean score and the standard deviation. So the probability distribution shows that about 10% of those who take the test score 4 on the proficiency test, or the probability of making 4 on the proficiency test is 0.1. With the same process of calculating the mean and variance, the mean score is 2, while the variance of score is 1.2, and the standard deviation of score is 1.095. After the expected value, variance, and standard deviation, let us now tackle the concept of the empirical rule. The empirical rule. The two key points with regards to the empirical rule. First, the data distribution must be approximately bell-shaped. Second, the percentages are only approximately true. So the empirical rule does not apply to data sets with severely asymmetric distributions, and the actual percentage of observations in any of the intervals specified by the rule could be either greater or less than those given in the rule. If a data set has an approximately bell-shaped relative frequency histogram, then approximately 68% of the data lie within one standard deviation of the mean. Approximately 95% of the data lie within 2 standard deviations of the mean, and approximately 99.7% of the data lies within 3 standard deviations of the mean. So this is the graph that shows the empirical rule. It is a bell-shaped data distribution with approximate 68%, 95%, and 99.7%. Aside from the empirical rule, let us discuss the concept of Chebyshevs Theorem. The Chebyshevs Theorem. The Chebyshevs Theorem gives the minimum proportion of the data which must lie within a given number of standard deviations of the mean. To calculate the proportion, the formula is 1 minus 1 over k squared. If k is not given, you can calculate it by subtracting the mean from the random variable x and then dividing it by the standard deviation. For any numerical data set, at least 3/4 of the data lie within 2 standard deviations of the mean. At least 8/9 of the data lie within 3 standard deviations of the mean, and at least 1 minus 1 over k squared of the data lie within k standard deviations of the mean. So this is the graph that shows the Chebyshevs theorem. It is not a bell shape because it is an asymmetric distribution. Let us know the difference between the empirical rule and the Chebyshevs theorem. First, the empirical rule is an approximation that applies only to datasets with a bell-shaped relative frequency histogram. It estimates the proportion of the measurements that lie within 1, 2, and 3 standard deviations of the mean, while the Chebyshevs theorem is a fact that applies to all possible datasets. It describes the minimum proportion of the measurements that lie massed within 1, 2, or more standard deviations of the mean. Second, the empirical rule is being applied to normal or symmetric distributions, while the Chebyshevs theorem is being applied to unusual or asymmetric distribution that works for any type of distribution. Example: the daily production of electric motors at a certain factory average 120 with a standard deviation of 10. A. What fraction of these will have a production level between 100 and 140? B. Find the shortest interval certain to contain at least 90% of the daily production levels. Because no information about the shape of the distribution of daily production levels is available, we'll use Chebyshevs theorem to answer these questions. First, we must find the distance between 140 and the mean, which is 120, in terms of standard deviation of the distribution as follows. So k is equal to 140 minus 120 over 10 is equal to 2. Using Chebyshevs theorem with k is equal to 2, so 1 minus 1 over 2 squared is equal to 3/4 or 75%. It shows that at least 75% of the days will have total production in this interval. To find k, we must set 0.9 equals 1 minus 1 over k squared and solve for k. The value of k will be 3.16. From the formula mean minus k times standard deviation to mean plus k times standard deviation, the interval is 88.4 to 151.6. Therefore, we can say that the interval 88.4 to 151.6 will contain at least 90% of the daily production levels. So that ends my discussion about the topic of expected values of random variables. Again, I am Danica Villacrusis of BSEE 2A.